Okay, so now we're looking at question 2. Mark has to invent and build a number of devices. One involves the creation of a flywheel to conserve rotational kinetic energy. His first flywheel has a rotational inertia of this, so that's rotational inertia, that's I. He speeds it up from rest to 302 radians per second, that's omega f. And here, from rest means omega I equals 0 by applying a constant torque of 75 Newton meters. So that's tau. Show that the angular acceleration achieved is 321 or 0.321 radians per second squared. So we have I and tau, and we have this relationship between I and tau that gives us alpha. Alpha is equal to the torque applied divided by the rotational inertia, which gives us 75 over 234, which gives us 0.3205, which is equal to 0.321 radians per second, which is what we wanted to show. Whoops, radians per second squared. Calculate the number of turns the flywheel turns through to attain 302 radians per second. So this is a kinematic problem. It's a constant angular acceleration problem. So we have alpha equals 0.321. We have omega I equals 0, omega f equals 302. And we want to find theta. Theta will give us a number of radians. We're then going to need to divide that by 2 pi to find the number of turns. Okay, so we need to find the relevant equation that involves theta, alpha, omega I, and omega f, and that's this one. So we know that omega f squared is, sorry, not there. That's what we're trying to find. Omega f squared is equal to omega I squared plus 2 alpha theta. So rearranging this for theta, we get theta is equal to omega f squared minus omega I squared over 2 alpha, and omega I is 0, so we just get theta is equal to 302 squared over 2 times 0.321, which is equal to 142,062. 142,062 radians. So number of turns is equal to theta over 2 pi, which equals 22,609 turns. For part C, it says, describe and explain the design change that would allow him to construct the second flywheel, which has the same rotational inertia as the original, and comment on whether this change will affect the rotational kinetic energy of the wheel. Okay, so we want the same rotational inertia as the original and operating at the same angular velocity. Okay, so if that's the case, then we can say I is unchanged, omega is unchanged, and as EK rotational is equal to half I omega squared, EK rotational must remain the same. So I've done the easy part first, which is explaining on whether it would change the rotational kinetic energy. The second part here is that we want to say how we can do it with less mass. I is equal to mr squared, where r is the effective radius. If m is reduced, the effective radius needs to be increased to keep I the same, to keep I constant. This can be achieved by concentrating the mass closer to the rim of the flywheel, e.g. using a hollow wheel. Okay, so that's a full explanation that answers that question. All right, the last part of this question says, a small rotating spacecraft is floating freely in space. Its angular velocity can be changed by withdrawing or expanding the bars in the side using a small electric motor mounted inside the device. See below. Explain using physics principles how the spacecraft can be made to double its angular velocity, how this will affect its rotational kinetic energy, and whether energy is conserved within the spacecraft, and how energy is conserved. Okay, so how can it be made to double its angular velocity? So we can say, as there are no outside torques acting on the system, angular momentum L is conserved, i.e. Li is equal to Lf, or I omega I is equal to If omega F. To double omega, we need to have I. So we can achieve this by withdrawing the bars which will reduce the effective radius as I is equal to mr, I'll add a little effective there, mr effective squared. If r effective is reduced, I will decrease. So now we've explained how we can double its angular velocity. So we then want to talk about how it will affect its rotational kinetic energy. So we can say if I is halved and omega is doubled, we see that EK rotational will double. And we see that by going, so if we have EK initial equals half I initial omega initial squared, and EK final is equal to half times half I 2 omega I squared. So we've now doubled the initial angular velocity and halved the initial rotational inertia. We get a half times a half times 4 I initial omega initial squared. So we squared the 2, we multiplied out the half. Half times 4 is just 1. So that's equal to I initial omega initial squared, which is equal to 2 E K initial. Energy is conserved. So we're now looking at the third point. The extra kinetic energy has come from work done by the electric motor and obviously the electric motor uses some form of energy. It might be a solar cell on the outside, or it might be some batteries on the inside. Okay. So maybe we should add that as well. Which could have come from a battery, for example. Okay, so that's question 2.